In science, we push the limits of what's possible, always seeking to prove the impossible. But just because something isn't proven yet doesn't mean it's not real. Consider black holes, for example. We've known about the theoretical existence of these dark, powerful entities for over a century, from the insights of Carl Schwarzschild, who saw their potential within the framework of general relativity back in 1916, to John Michell, who predicted them based on Newtonian physics in 1783. For nearly 2 centuries, we pondered these strange objects, but it wasn't until 1971 that we saw the first confirmed black hole, Cygnus X1. For decades, we lived in a world of speculation, but the discovery of Cygnus X1 shook the scientific community. We knew black holes existed, but that was just the beginning. From there, we ventured into the realm of the unknown. What if there are other exotic objects hiding in the vast expanse of the universe, waiting for us to find them? What if there are stars we've never even dreamed of? Stars so bizarre and unlike any we've encountered that they could be lurking just beyond our detection. Welcome to Astrum. I'm Alex McColgan, and today we're delving into the mysteries of the universe. We'll explore some of the strangest phenomena that could be out there waiting to be discovered, and who knows, in 188 years we might know for sure. But for now, these are ideas based purely on theory with very little to show for them, except for the tantalizing possibility that one day we might uncover the unimaginable. Let's start by turning our attention to stars, the most captivating and awe-inspiring objects in the universe. Stars are born from clouds of gas, fused together by gravity, igniting a thermonuclear furnace at their cores. The energy produced by this fusion powers stars, emitting light and heat across the cosmos. They give life to planets, nourish the elements necessary for life, and ignite the very fabric of our universe. Through mergers, explosions, and the violent death of stars, we have been blessed with the heavy elements that make up the building blocks of everything around us. Astronomers have spent centuries studying the life cycle of stars. We know how they are born, how they evolve, and how they die. The fate of our own sun is already mapped out. It will eventually run out of hydrogen, expand into a red giant, and then collapse into a white dwarf. But while we understand the basics, there are other stars in the universe that defy our understanding. Stars so strange, so elusive, that they exist only in the pages of theoretical physics. But what if I told you that some stars could be made of vacuum? Yes, you heard that right, vacuum stars. Before we get there, we need to understand the basics of how stars work, so let's start with the sun, the most important star in our lives. The sun is made of gas, not solid matter. You can't walk on its surface the way you would on Earth. Its gravity would pull you in until you were crushed into its core. But here's the thing. The sun doesn't collapse inward. Why? Because there's a force pushing outward from its core, balancing the pull of gravity. This force comes from the radiation produced by fusion reactions, and this radiation pressure is just enough to keep the gas from collapsing under its own weight. This balancing act between gravity and radiation pressure is present in all known stars. It's what keeps them stable. The sun shines brightly because it's fusing hydrogen into helium at its core. But one day, that fuel will run out. When that happens, the sun will expand, becoming a red giant, and begin fusing heavier elements like helium into carbon and oxygen. Eventually, the sun will collapse into a white dwarf, a stellar remnant where fusion no longer occurs. But here's the real mystery. Without fusion, what keeps a white dwarf from collapsing into a black hole? That's where quantum mechanics enters the scene. When the core of a dying star becomes a white dwarf, its density increases to the point where something incredible happens. Electron degeneracy pressure. Electrons, the fundamental particles that make up atoms, can't occupy the same space. This creates a kind of pressure that resists further collapse. But even electron degeneracy pressure has its limits. If a white dwarf's mass exceeds a certain threshold, it can no longer support itself and begins to collapse further, eventually becoming a neutron star. Neutron stars are the densest objects in the universe, save for black holes. They're supported by neutron degeneracy pressure, which is even stronger than electron degeneracy pressure. But even this pressure has its limits. If a neutron star becomes too massive, it will collapse in on itself, and the result is a black hole. The point of no return. A place where even light cannot escape. But what if there was something more powerful than neutron degeneracy pressure? Could there be stars that are even denser than neutron stars, yet somehow avoid turning into black holes? That's where things get truly wild. Physicists started theorizing about stars made of exotic matter, matter with negative pressure, something that could theoretically provide even greater support against gravity. If these stars existed, they would be smaller and denser than neutron stars, but they wouldn't collapse into black holes. In fact, they could mimic the appearance of black holes, but they wouldn't have the defining characteristic of a black hole: the event horizon. Now, imagine a star with a pressure that behaves in ways we've never seen before. It might even have a negative pressure at its core, balancing out the inward pull of gravity with a push outward. If this happens, the result is a gravitational vacuum star, or Gravastar for short. These exotic stars would have properties so bizarre that they would challenge everything we thought we knew about stellar objects. Inside of a Gravastar, there would be no gravitational force. The positive energy and negative pressure would cancel each other out. It would be like being inside a vacuum, floating freely without being pulled in or pushed out. But there's a catch. As you move closer to the edge of a Gravastar, the pressure at the core flips from negative to positive, and eventually, you would reach a point where the Gravastar's size becomes indistinguishable from that of a black hole. At least, to an outside observer, it would look like a black hole, but it would behave very differently. No event horizon, no infinite density, just an exotic, strange object that could be scattered throughout the universe, waiting to be discovered. And here's where the true mystery begins. If Gravastars are real, could they be the key to understanding dark energy, the mysterious force that's been causing the universe to accelerate in its expansion? Some scientists believe that Gravastars could be made of dark energy, and that the very existence of these objects might be the answer to one of the greatest cosmic questions. But that's not all. We've only scratched the surface. In the next part, we'll dive deeper into the strange and mind-bending world of white holes and wormholes. As we venture deeper into the fabric of the universe, we reach a place of curiosity that challenges everything we know about black holes. These elusive, enigmatic objects are some of the most puzzling features of our universe. But what if I told you there's a counterpart to the black hole? An opposite, a force that pushes outward instead of pulling inward? Something so strange that it could rewrite the very nature of space-time itself. This counterpart is called a white hole. Let me take you on an intellectual journey, beginning with a simple analogy. If I ask you to picture a cone, you probably envision something like a traffic cone pointing upwards, or perhaps an ice cream cone pointing downwards. In the real world, we typically think of cones as having a singular direction, up or down. But the mathematical description of a cone is far more complex. It has two halves, one that points up and another that points down, joined together at their tips. Now, apply this concept to black holes. We understand black holes in a similar way. A black hole, in the mathematical sense, is an object that has formed by the collapse of a massive star under its own gravity, leading to a singularity at its core, where all matter and energy are crushed to an infinitely dense point. Surrounding this singularity is the event horizon, a point of no return. Once something crosses the event horizon, it cannot escape. Not even light can break free from the crushing gravity. But imagine for a moment if the mathematics describing a black hole were only part of a larger whole. A two-way structure that mirrors the black hole's pull with an equal and opposite force. What if the event horizon of a black hole also had a twin, an area where light and matter could only be expelled, but never pulled in? This idea leads us to the concept of white holes. In a white hole, the gravitational force would work in reverse. Instead of pulling everything inward like a black hole, a white hole would push matter and light outward. If black holes are where the universe's secrets get hidden and lost, white holes would be places of creation, releasing energy and matter into the universe. The inverse of a black hole, a white hole could be just as real, though far more elusive, and in many ways they provide more questions than answers. One of the key differences between a black hole and a white hole is their relationship to time. In a black hole, time appears to slow down as you approach the event horizon. To an outside observer, it seems as though time stops altogether when something reaches the singularity, and that's because light, the fastest thing in the universe, can no longer escape. But for a white hole, time would behave differently. Everything would be ejected, spewed outward like a fountain of creation, flowing toward us from the past. A white hole doesn't just exist as a destination for objects to be swallowed. It's a continuous source, a temporal wellspring of energy and matter. To further understand how these objects fit into the framework of spacetime, we must turn to the Penrose diagram, a mathematical tool used to visualize black holes and the flow of time and space around them. In a traditional black hole, the Penrose diagram shows a one-way journey toward the singularity. Once something crosses the event horizon, there's no coming back. It's a one-way trip toward destruction. But for a white hole, the diagram is flipped on its head. Instead of an inward pull, it has an outward expulsion, where light and matter flow freely from the white hole's singularity, never to be drawn back in. Imagine standing at the event horizon of a white hole and watching a stream of particles and light shooting outward from the heart of it, traveling backward in time, creating new material that can never be recaptured. It's as if the universe is constantly being created anew, with no end in sight. This mirror image concept doesn't just challenge our understanding of black holes. It also introduces the possibility of new dimensions. According to some physicists, if white holes exist, they could be connected to parallel universes. The white hole would be the boundary between our universe and another one entirely, forming a bridge between them. This is the essence of what's known as a wormhole, a passage through spacetime that connects two different points in the universe. Now, before you dismiss this as pure science fiction, consider this: the mathematical principles that govern black holes and white holes come from the same equations. They're both grounded in the framework of general relativity, a theory that has withstood nearly a century of scrutiny and observation. There's no reason why white holes couldn't exist in the same way black holes do, even if they are much harder to detect. But the biggest question remains: if white holes do exist, how do we find them? Unlike black holes, which are detectable because of the way they bend light and pull in nearby matter, white holes would not exhibit the same gravitational signature. They would emit bursts of energy and matter, but they wouldn't exert any gravitational pull, making them nearly invisible to our current detection methods. Perhaps they are too fleeting, too short-lived, to be observed directly. Or perhaps they are out there, tucked away in the fabric of spacetime, waiting for us to find the right clues. While we're on the subject of invisible phenomena, let's move forward to another mind-bending idea: wormholes. The concept of wormholes, or shortcuts through spacetime, has long been a staple of science fiction. But as we continue to probe the universe, we find that the mathematics behind wormholes is just as real as the equations governing black holes and white holes. In theory, a wormhole could provide a tunnel from one part of the universe to another, bypassing the vast distances of space in between. Picture it like a tunnel through a mountain. Instead of driving around the mountain, you simply enter the tunnel and emerge on the other side in a fraction of the time. Wormholes, if they exist, could allow us to travel to distant parts of the universe in a matter of moments. The real question is whether we could ever cross them, or if they are as theoretical as the concept of white holes themselves. Now that we've explored the strange and fascinating realms of white holes and gravastars, it's time to delve into one of the most profound and perplexing concepts in modern physics: wormholes. These theoretical shortcuts through spacetime could potentially allow us to travel vast distances in the blink of an eye. But the more we examine these possibilities, the more we realize that they could offer much more than just faster travel through space. They might hold the key to unlocking entire new dimensions of reality. A wormhole, in its simplest form, is a passage or tunnel through spacetime that connects two distant points in the universe. Imagine a vast sheet of paper representing the universe, with 2 points drawn on it. Normally, if you wanted to travel between these 2 points, you would have to traverse the entire length of the paper. But what if you could fold the paper, bringing the 2 points together? This fold, in essence, would be a wormhole. It would create a shortcut, a direct route from one side of the universe to the other. The theoretical foundation for wormholes comes from the equations of general relativity, and they are often depicted as Einstein-Rosen bridges. These bridges connect two separate regions of space, creating a path that cuts through the fabric of spacetime. But while the mathematics behind wormholes is sound, the physical reality of such a structure is far more complicated. One of the most significant challenges with wormholes is that they are incredibly unstable. Theoretical physicists have long debated the conditions necessary to keep a wormhole open. Without a special form of exotic matter that possesses negative energy, a wormhole would collapse almost instantaneously, preventing anything from passing through it. This exotic matter would need to exert a repulsive force, keeping the wormhole's walls from collapsing in on themselves. But the question remains, does such exotic matter exist? And if so, how could we harness it? Some scientists speculate that the very fabric of spacetime might contain fluctuations in energy, tiny pockets of negative energy that could, in theory, stabilize a wormhole. However, this idea is purely speculative, and no one has yet observed negative energy on the scale required to keep a wormhole open. For now, wormholes exist only as a mathematical curiosity. However, the possibility of traversing them opens up a plethora of tantalizing ideas. Could wormholes act as time machines? Could they allow us to travel not just across the universe, but back in time or to alternate timelines? The implications are staggering. The ability to travel through wormholes could fundamentally change our understanding of causality and time itself. But before we get too carried away with the idea of time travel, we must take a moment to consider the physical constraints of wormholes. Even if we were able to create or find a stable wormhole, there are several challenges that make it nearly impossible for us to traverse them. For one, wormholes are incredibly small on the quantum scale. If they exist, they are likely to be minuscule, too tiny for any human or spacecraft to pass through. Additionally, if we could somehow stretch or enlarge a wormhole to a size large enough for travel, we'd need to contend with the immense gravitational forces at the entrances and exits. These forces could tear apart anything attempting to pass through, including light itself. So, what's the reality behind wormholes? Are they merely a theoretical concept that will remain confined to the realm of science fiction? Or could they one day become a practical tool for intergalactic exploration? While the jury is still out on this question, one thing is clear. The idea of wormholes challenges our current understanding of space and time. The possibility that there could be hidden shortcuts in the fabric of the universe is an exciting thought, but it also raises new questions about how we perceive reality itself. As we move forward, let's shift our attention to something even more mind-bending: parallel universes. The idea that our universe is just one of many, existing alongside countless others, has captivated physicists for decades. In fact, the concept of parallel universes, often referred to as the multiverse, has become one of the most intriguing and controversial ideas in modern cosmology. The multiverse theory suggests that our universe is just one of many, each with its own unique properties and physical laws. These universes could exist in different dimensions, with some so far removed from our own that they may never be accessible to us. Imagine a vast, infinite sea of universes, each one distinct from the others, each one containing its own version of reality. Some universes might have different constants of nature, such as a different value for the speed of light or the gravitational constant. Others might have entirely different physical laws, where concepts like time and space are radically different from anything we can imagine. But how can we know if such universes exist? After all, the multiverse theory suggests that these universes are completely disconnected from our own, making it nearly impossible for us to observe them directly. In fact, the very nature of parallel universes means that we are fundamentally separated from them, unable to communicate or travel between them. Despite these challenges, some physicists argue that the multiverse theory could provide an explanation for some of the most perplexing questions in physics. For example, the fine-tuning problem, the question of why the constants of nature in our universe seem to be perfectly set to allow life to exist, could be resolved by suggesting that there are countless universes, each with different physical properties. In some universes, the constants of nature would be unsuitable for life, but in others, they would be just right. One of the most compelling aspects of the multiverse theory is its connection to quantum mechanics. According to the many worlds interpretation of quantum mechanics, every quantum event, every measurement or observation, splits the universe into multiple branches, each representing a different outcome. In this view, the universe constantly branches into multiple realities, each one containing a different version of events. The many worlds interpretation suggests that every time we make a decision, we create a new universe in which a different version of ourselves exists, living out a different possible outcome. The implications of this theory are profound. If the many worlds interpretation is correct, then there are an infinite number of parallel universes, each one containing a version of you making a different decision. You could be living in countless parallel worlds, each one with its own unique history and future. But how do we test this theory? How can we ever prove the existence of these other universes, let alone interact with them? For now, the multiverse remains a fascinating but unprovable idea. While there is no direct evidence for the existence of parallel universes, the theory provides a tantalizing explanation for some of the most mysterious aspects of our reality. And while we may never be able to visit these alternate worlds, the very idea that they could exist changes the way we think about the universe and our place within it. As we explore these strange possibilities, wormholes, gravastars, white holes, and parallel universes, one thing becomes clear. The universe is far stranger and more complex than we ever imagined. The theories and ideas we've discussed here are just the beginning. The mysteries of the cosmos are waiting to be uncovered, and it's only a matter of time before science catches up with the ideas that once seemed like mere speculation. The future of exploration is limitless, and the answers to these profound questions could reshape our understanding of reality itself. But there's one last, lingering question that remains. What if all of this is just a glimpse of something even greater? What if our universe is only a small part of an even more vast and incomprehensible multiverse, one that stretches across dimensions we cannot yet perceive? The possibilities are endless, and the journey has only just begun. Now that we've ventured through the twisting concepts of gravastars, white holes, and wormholes, we've scratched the surface of the unknown mysteries that could lie beyond our universe's observable boundaries. But even with these exotic objects, the grandest questions remain unanswered. Could the fabric of the universe, the very space and time in which we exist, be far more intricate than we have ever imagined? Could there be layers of reality beyond our perception, invisible yet fundamental to the structure of everything? Let's begin by expanding our understanding of the multiverse theory and its connection to the deepest questions in physics. Until recently, the idea of a multiverse, an infinite set of universes, each with different physical laws or constants, was relegated to the realm of science fiction. But recent developments in theoretical physics have shown that this seemingly far-fetched notion might be closer to reality than we ever thought. Imagine a collection of universes, each one a bubble within a greater cosmic sea. Some of these universes might have very similar properties to ours, while others could operate under completely different rules, governed by unique physical laws that are impossible for us to comprehend. One of the most fascinating concepts to emerge from the multiverse theory is the idea of bubble universes. These bubbles are thought to form from fluctuations in a field known as the inflaton field, which is theorized to have driven the rapid expansion of the universe during the period of inflation just after the Big Bang. In this model, each bubble universe is formed from a tiny pocket of spacetime, where different physical constants and properties take shape. These universes could be vastly different from our own in terms of their size, structure, and laws of nature. But here's the kicker. If these bubble universes exist, they might be forever separated from our own. They could be so far removed in both space and time that no light or matter from one could ever reach the other. In this case, our universe would be a mere speck in an infinite sea of universes, each one hidden behind the veil of its own cosmic horizon. This raises a profound question. What happens when the boundaries between these universes collide? Could they influence each other in ways we can't yet comprehend? And if they can't interact, does that make them any less real? The implications of this are staggering. If the multiverse theory is true, then everything we've ever known, every galaxy, star, and planet, could be part of a much larger and more complex network of realities. And it's possible that the very laws that govern our universe are just a fluke, a random set of conditions that allowed life to arise here and now. As improbable as it may seem, this fine-tuning of the universe's physical constants could be the result of an infinite number of universes, each with its own unique set of rules. In this cosmic lottery, we just happen to be born into the one where life can exist. But there's more to this story than just the multiverse. Let's take a step further into the unknown by considering the possibility of higher dimensional spaces. Our universe, as we know it, is governed by 3 spatial dimensions and 1 time dimension. But what if there are more dimensions beyond the 4 we can perceive? What if the true nature of reality exists in higher dimensional spaces, hidden just out of reach? This concept is central to theories like string theory and M-theory, which propose that the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to the particles and forces we observe in our universe. According to string theory, there could be as many as 11 dimensions in total, though only 4 of them, 3 spatial and 1 time, are accessible to us. The other dimensions, curled up in a way that we cannot perceive, could be the key to understanding the fundamental nature of reality. But how would we even begin to detect these extra dimensions? The answer, surprisingly, might lie in the energy of black holes. Some physicists believe that the study of black holes, particularly their event horizons, could reveal clues about the higher dimensional spaces in which they exist. As black holes warp the fabric of spacetime, they may also be influencing hidden dimensions in ways that we can only begin to comprehend. If we could somehow observe the behavior of matter and energy around a black hole, we might uncover evidence for these extra dimensions, providing a glimpse into the true nature of reality. As we explore these strange new ideas, we also find ourselves contemplating the nature of time. Time, as we experience it, flows in one direction, from past to present to future. But is time truly as linear as we think? Could it be that time, in some higher dimensional sense, is a more malleable concept than we realize? This question has led to one of the most mind-bending hypotheses in physics: time travel. If the fabric of spacetime is more flexible than we think, could it be possible to travel backward in time, or even to step into an entirely different time period? Theoretical physicists have long speculated about the possibility of time loops, wormholes, and closed time-like curves, CTCs, paths through spacetime that allow an object to return to its own past. In some interpretations of quantum mechanics, time is not a one-way street but a multidimensional, flexible concept that can be manipulated under the right conditions. Imagine the consequences of such a discovery. If we could travel backward in time, we could witness the birth of stars, the rise and fall of civilizations, or even interact with versions of ourselves from the past. But time travel comes with its own set of paradoxes. What happens if we change the past? Would the future we know still exist? Would we create an entirely new timeline? The possibilities are endless, and while time travel remains purely theoretical, the question of whether it could one day become a reality is one that continues to intrigue and puzzle physicists. But as we push the boundaries of physics and contemplate these incredible possibilities, we must also ask, what does all of this mean for us? If wormholes, white holes, higher dimensions, and time travel are indeed possible, what does that say about our place in the cosmos? Are we simply part of an infinite web of universes, existing in a fleeting moment in time, or are we at the center of something much greater, something that transcends space, time, and reality itself? The answers to these questions are still beyond our grasp, but that doesn't mean they won't one day be discovered. Science has a long history of turning the impossible into the possible, of transforming theoretical concepts into tangible realities. As we continue to explore the universe, we may one day unlock the secrets of dark energy, discover the truth about parallel universes, or even step through a wormhole into a new dimension of existence. The journey of exploration is far from over, and the mysteries of the universe are waiting for us to uncover them. Who knows what strange and jaw-dropping phenomena will emerge as our understanding of physics continues to evolve. Theoretical landscapes of space and time are brimming with possibilities, and it's only a matter of time before we discover what lies just beyond the stars. As we reach the final chapter of our cosmic journey, the mysteries of the universe have unraveled in ways we never thought possible. We've explored the theoretical landscape of exotic stars, wormholes, gravastars, white holes, and even ventured into the mind-bending possibilities of parallel universes and higher dimensions. Now, we face the most profound question of all. What does all of this mean for us? As humans, we've spent millennia looking to the stars, trying to understand our place in the universe. And perhaps, as we continue to break the boundaries of our knowledge, we are inching closer to a truth that transcends space, time, and everything we thought we understood about reality itself. The universe is vast, almost unfathomably so, and it's filled with forces that stretch our imaginations to their limits. We've explored the idea of multiverses, an infinite array of universes, each with its own set of rules. This brings us to the ultimate realization. The universe we see around us, the one in which we exist, might be just a small piece of a much grander, infinitely complex puzzle. Perhaps, within the vast sea of parallel universes, there are realities so radically different from our own that they seem utterly alien, even to our most sophisticated theories. What if we are only a fleeting moment in the timeline of an eternal cosmos, where each choice, each quantum fluctuation, gives birth to an entirely new universe? What if everything we know, the stars, the galaxies, the black holes, and even time itself, is just one expression of a larger, unfathomable truth that transcends the limits of human perception? The more we delve into these theories, the more it becomes clear our understanding of the universe may be fundamentally incomplete. We may be living in a reality where the rules we take for granted, such as the passage of time and the behavior of matter, are just a small facet of something much more complex. Perhaps the nature of existence itself is not just about what we can see and measure, but also about what we can't. The idea of a multiverse, for instance, challenges the very notion that our universe is the only one that exists. In fact, the multiverse suggests that there could be infinite versions of reality, each one playing out different scenarios, each one governed by its own laws of physics, constants, and fundamental properties. In one universe, gravity might behave differently, or light might travel at a different speed. In another, the very fabric of space and time might be altogether different. The implications of such a theory are staggering. Could the choices we make have counterparts in other universes, where different versions of ourselves are living out different lives? If so, are we simply a fleeting moment in a larger cosmic web? Or is there a deeper meaning behind the infinite possibilities that exist within the multiverse? At the heart of the multiverse theory lies a question that we may never fully answer. Why us? Why does this particular universe, with its precise constants and laws, allow life to arise and evolve? Why is the dark energy density in our universe just right to permit the formation of galaxies, stars, and planets, and by extension, life itself? The odds of the universe being fine-tuned to allow life as we know it are so small that it seems almost impossible. Unless, of course, there are countless other universes, each with its own set of rules, and we just happen to be in the one where life could exist. In this view, our existence is not a miraculous accident but the result of an infinite number of attempts, where the conditions just happen to be right in our universe. This line of thinking brings us to one of the most profound implications of the multiverse theory: the idea of cosmic purpose. If there are an infinite number of universes, each one with different physical laws, could there be a deeper meaning behind our particular reality? Are we simply a random occurrence? Or is there something inherent in the structure of our universe that leads to life, consciousness, and the search for meaning? The answer to this question remains elusive, but the very fact that we can ask it speaks to the extraordinary nature of our existence. But as we explore these possibilities, we must also confront the limitations of our understanding. We've touched on the idea of higher dimensions, those beyond the familiar three spatial dimensions and one time dimension that govern our everyday lives. What if the true nature of reality exists in these higher dimensional spaces, spaces that we can neither see nor comprehend? Theories like string theory and M-theory suggest that the fundamental building blocks of the universe are not particles but tiny, vibrating strings that exist in up to 11 dimensions. These extra dimensions could hold the key to understanding the true nature of spacetime and the fundamental forces of the universe. But until we can detect these dimensions, we are left to imagine what they might look like. Moreover, we've explored the tantalizing possibility of time travel, an idea that has captivated the human imagination for centuries. If wormholes exist and could be stabilized, could they serve as a portal through time as well as space? The idea of traveling backward in time, of visiting the past or the future, is a concept that has fascinated both scientists and philosophers. But as we've seen, Time travel brings with it paradoxes that defy logic and challenge our understanding of causality. Could we ever travel to the past and change the course of history? And if we did, would we create an entirely new timeline, one that diverges from our own, or would we erase our own existence entirely? The concept of time itself may be more malleable than we've ever realized. We've long assumed that time flows in one direction, from past to present to future. But as we venture further into the unknown, it becomes clear that time may not be as fixed as we once thought. Could time itself be a construct, a feature of our perception, rather than a fundamental property of the universe? If so, what does that mean for our understanding of reality? As we reach the end of this journey, we are left with more questions than answers. The universe is far stranger and more complex than we could ever imagine. From wormholes to parallel universes, from black holes to white holes, the possibilities for discovery are endless. Yet, with each new breakthrough, we realize just how little we truly know. The more we learn, the more we uncover new mysteries that challenge the very fabric of reality itself. But here's the most profound truth of all. The quest for understanding, for uncovering the secrets of the universe, is not just about finding answers. It's about embracing the unknown. It's about pushing the boundaries of human knowledge, daring to ask questions that have no easy answers. And in that pursuit, we are reminded of the wonder and awe that come with contemplating the vast, infinite cosmos. So where do we go from here? The journey of exploration is far from over. The universe is vast, its mysteries deep, and the discoveries yet to be made are beyond our wildest dreams. We stand at the edge of the unknown, ready to explore the deepest corners of reality. And as we continue our search for answers, we can be sure of one thing. The future holds unimaginable discoveries, and the wonders of the cosmos are just waiting for us to uncover them.